we good to go? Yeah. Okay. So hello everyone. This is HDF 3.11 for work groups. No, that's a joke. Peter Wang's joke, so I take no responsibility for it. This is actually HDF5 is for lovers. My name is Anthony Scopatz. I'm a postdoc at the University of Chicago, former and butter, and I'm going to be talking to you about. Or originally, this presentation was mostly about how to get HDF5 to work with, sort of integrated into your workflow and work with other databases and things like that. But well, I'll get into this in a moment. So, okay. So what is HDF5? It stands for Hierarchical Data Format 5. And it's written by the people at the HDF group. You can see they're very creative with their names. And they're a group out of the University of Illinois at Champaign-Urbana. So, but what HDF5 actually is it's this binary file format. And it's a pretty sophisticated binary file format, in fact. So there's a lot of nice features here. And there's just a ton of libraries that it interacts with, and people do things with this all the time. And we'll sort of talk about why HDF5 has risen to the heights of sort of binary databases. And you're going to get to learn all of that today, or at least some of it. So the format of this tutorial, you guys, how many people were in Eric's session earlier this morning? Okay. So I know how Eric teaches. We're going to do something very similar. There's going to be sections where I'm sort of presenting on the slides. Then there are going to be parts too where I encourage you to type while I'm talking and work and type up with questions and all that stuff. And then there's going to be sections on exercises where I'm going to walk around and try to help you guys if you run into problems. But yeah, definite interaction is a positive. So, in that, yeah, feel free, ask questions whenever, and also feel free to explore the documentation and everything else at your own pace. And originally this tutorial was submitted to the advanced track, and it was also slated to be after the IPython tutorial. So we got moved around. So my original vision of what this was going to be has changed to be an intermediate or a beginner to intermediate talk, and I'm not going to use any of the IPython features, And so what do? We get the program committee. Actually, they're all nice people. And Dart Hospital telling me. So. Okay, so let's just ask a couple of quick questions. How many people have used HDF5 before? Just by a show of hands, like everyone raising their hand. Okay, so it looks like about half the class maybe. How many people have used pi tables before? Looks to be about the same half. So. How many people have used H5Py? A couple people, yeah, okay. How many people have used the HDF5C or Fortran or C++ APIs? Okay, one or getting down here. How many people have used SQL in any way, shape, or form? Okay, that's good. That's almost the whole class. And how many people have used other binary database formats? Okay. Technically, this should be everyone, right? Okay. So how we're going to do this? Thanks. That gives me a good sense of where people are. First, what we're going to do is, does everyone have pi tables installed already in some way, shape, or form? If you're no shame, please raise your hand and let us know.
If we have it or if we don't. If we have it or if we don't.
If you don't have it, raise your hand. Okay. So, it looks like there's just a few people. We have a strategy for you. What's your issue? Do you not have a version of EPD? That'd probably be the primary way to get it, I would think. You're on Mac OS? Okay. Well, you can get HDF5 and all of the other dependencies, I'm pretty sure, through Mac ports. Maybe Darhas can... And that's for Mac?
Yeah, it's just,
okay.
just look it up.
Yeah, and,
Okay, SciPy Super Pack. Oops, sorry.
Oh, I was going to say also Homebrew does the trick too. That's what works.
Okay, or any of these package managers, right? So like, ideally your package manager will have it. In your case, sir, your package manager doesn't have it, but if you grab the dependencies, you should be able to go to this website, this github.com, or shoot, sorry, no, this is the wrong SciPy. So let me go over here. If you go to the PyTables documentation, which if you can read this is up at, it's pytables.github.com. It should tell you there is this downloads link, and you should be able to easy install or pip install it if you have either of these. But it will require that you have the dependencies as well. And if you still don't have it by our first exercise or second exercise, I'll come around and help you get that installed. Okay. So the next thing that I want you to do is actually, for the purpose of this class, and so that you have our exercises, here's a question I missed, but who has Git installed? Or knows how to use Git? Okay, so please just clone this repo for this class. Or alternatively, just go to this website, which may or may not open, and aha, it did. And just download the zip or tarball from this website and unzip that on your hard drive somewhere. Okay, and I'll give you guys like a minute or so to do that. Put this back on. Super exciting. Doesn't seem big enough. Yeah. Sorry, this is the address. Can you guys see this? Is this a large enough font? Okay. I'm neurotic about font sizes during presentation. Do most people have this now? And it's,
Do you know how to get HDF5 on a Mac?
through any of the package managers, or this gentleman was saying, what was SciPy Super Pack?
Yeah, especially online.
Are people pretty much in this work? Okay, we're going to move on then. And start with a warm-up exercise just to make sure that everything's functioning. So either in IPython, or you can go to the HDF5, so go to that repo that you just cloned, go to the HDF5 subdirectory, and then go into the exercise or excerpt directory, and just run warmup.py, or type this into IPython, and make sure that it runs successfully. And if it doesn't run successfully, then we have other problems, and we'll come around and talk. But that's the purpose of this point. So, oops. The other thing I mentioned in the talk notes is that if you can install VI tables, that would be really beneficial, or HDF5. So I'll just take you to the website here. These are viewers for HDF5 files. So this is VI tables, and then HDF5 is here. And I'm going to be using them throughout the course, so if you want to use them too, please install them. So the first one is VI tables. This is what I use. It's written in Python. HDF5 is written in Java. So take your pick. Did anyone have trouble getting this warm-up exercise to run? Or yeah.
Different question. What version of VI tables do you recommend?
It doesn't much matter which version of VI tables you use. It is on GitHub, so you could get the latest version. It hasn't been updated in 8 months, so it's pretty stable. It's also in many Linux package managers too. So. Okay, did this run for everybody?
No, not yet.
Not yet?
It's like you need 2 screens.
Yeah, I was hoping there was going to be another machine, but alas, I only have one lap to top. Yeah, it wasn't my best joke. There will be better, I promise. Well, I leave that to you to decide. There should be a panel with people with numbers in the back. Yeah, is Paul not here at all? Oh, that's too bad. Okay. Yeah. So I'm going to go ahead and run this exercise myself just to show you VI tables. So when I ran that, it created this temp.h5 file, and then this is what VI tables looks like. And somewhere here. Okay. And then here's here's basically what VI tables does. So it's a nice viewer for your data. Oh. And this is what you get on the next slide. Okay, well, everyone, just a couple people still having problems, I think, right? Well, if you who are still having issues getting this to run could ask your neighbor until we get more time during the second exercise, that'll be great. And I'll just come back and help. Because I think, yeah, we're already 20 minutes in. So since this tutorial was recast as an introduction, I'm going to go over in sort of very basic details briefly what HDF5 is and sort of how PyTables interacts with it. So if you're a more experienced HDF5 user, please bear with me. And bear with me with some of these concepts at the beginning. But to start off, we'll say that, or I'll postulate that the binary data formats are better for storing numerical data than storing them as plain text. If for no other reason, that they are often smaller in size, right? The number of bytes that is needed to store the equivalent amount of data is actually much fewer than very long formatted float. So here, as you can see, right, so ints, they have this static size, at least in Python, they're either 4 or 8 bytes. When you store, with small ints, when you store them as a string, right, here, this is 2 bytes for a short int. However, longer ints, right, they still keep that same size that they can represent. So that's still 4 bytes, but as you add on digits to that, or characters to that string, the number of bytes increases linearly. And a similar situation happens with floats, especially if you're using exponential notation. You sort of always take this hit with this period and the e and the plus or minus, etc. So, if for no other reason, your data size on disk is going to be smaller and in memory. The other reason why storing numerical data in a binary format is superior is that these string to integer or string to float functions that you write are actually very, very expensive. They're not the simplest algorithms in the world. They're not overly complex either, but they do take a lot of time if you have to, for every single data point, run this code. They're a couple hundred lines long. If you go to Google and search for these, you can find at least 1,000 different implementations of these functions in various C libraries out there. So they all have varying levels of performance, but they're typically deemed as expensive as compared to just storing the raw bytes. Moreover, so you can imagine a world where you just take those bytes that you have in memory and store them out to this raw binary file. But typically, you want something a little more than that. Not that that's a bad idea, really, actually, at all. In fact, when you call numpy.save or numpy.savez, that's exactly what it's doing. It's storing a little bit of metadata in there as well, but it's pretty much just splitting that array right from memory to disk. So what HDF5 is it's an actual sort of database on top of all of that, and it gives you the ability to define user attributes and query the data and structure data sets in different ways. And you don't have to take care of that. That's what the library does for you. And there's optimizations in terms of I/O and things like that. And we'll get into each of these features as the tutorial goes on. But unlike SQL, where every data set sort of lives in this flat namespace, HDF5 or HDF really lets you nest these data sets in a tree structure. And so in effect, you can kind of think of HDF5 as being a file system for data within a single file, or within its database. We'll talk a little bit more about that in the future. Okay, so that said, what sort of data sets are available in HDF5? Well, the absolute most basic data set that you could possibly care about is equivalent to the NumPy array, but on disk. So it's just, there's an array class. On top of that, there's a thing called a chunked array. We'll get into what chunky means. There's also an extendable array, and in general, the extendable array can be added to infinitely along any dimension. There's a variable length array, or a ragged array, so where elements don't have to be the same size in terms of the number of bytes that they keep. And then finally, sort of the penultimate data structure that the package itself is named after is the table, which effectively, I'm hoping it's got to this last class, but this is basically a structured array with named fields. Did you guys cover structured arrays last?
We didn't get to them.
You didn't get to them. Okay, that's too bad. But well, you will be very familiar with them by the end of this lecture.
See, I knew that. So.
Yeah. You're a cunning individual. So much like NumPy arrays, all of the elements of these arrays or tables must be composed of atomic types. That said, there's a few different atomic types. These are very mappable from what NumPy has to what PyTables has, or what HDF5 has, or really basically how people think about data, binary data in general. So to start, there's a Boolean type. This takes up 8 bits, or 1 byte, right? So you might think you could get away with a single bit here, but in fact it stores a lot more. You need to do some extra fancy work to have bit maps and things to get this to take less space. There's a variety of integer types, the 32-bit being the default. There's unsigned integers, 32 again being the default. Float, 64 being the default. This is similar to Python and NumPy, etc. Complex data, and strings. There's a couple of other data types as well. There's a date-time data type and an enum type that we won't cover in too much detail here, but they do exist. So that's basically what you can, that's what your data sets are. Here's what they're composed of. There are other elements in the HDF5 hierarchy. So there are groups. These are equivalent to directories in your Unix file system analogy, right? So groups are other elements of the hierarchy that allow you to stick data sets or other groups inside of them. There are links, both hard and soft links, that can point from one node in your tree to any other node. There are file nodes, which unfortunately we don't have time to talk about in too much detail. And then there are hidden nodes. So they're in the same way that you might have hidden files or hidden directories, you can also have hidden data sets and hidden groups in HDF5. They're basically nodes without a name. And you can find all of this documentation at pytables.github.com. So please click on that link, or please go to this website, because for most of the exercises, you might need to explore the documentation simultaneously to doing it. The goal here is that you know how to use the tools that we've provided, so make sure you can get to this website. Okay. So that's it for our brief overview of what HDF5 is. Any immediate questions? Nothing too weird. Yeah.
Is it a server-based system like the SQL thing, or file-based?
No, it's file-based. So it's a file that you create.
But it's multi-user.
It can be. We'll talk more about that later. Okay, so how do you open one of these files? Well, there's an open files function. Ta-da. So here, if you go to IPython, right, you can just import tables, and I'm typically going to import that as TB, and open up any file. Well, we made an exercise file, so why don't I can try to go ahead and open that in my terminal here. I encourage you to all have IPython or something up and running simultaneously. I'm just going to import tables as TB, and then TB, or I should say F equals file. And then I had a temp, what's it called? Temp.h5. I'm just going to open that in read mode. And voila, you see I have this file object. Okay. Files can be opened in the sort of standard modes that you have in other places in Python. There's read-only, you can't modify the data. There's write. That means that basically this is equivalent to the CAPI truncation mode, where you get rid of everything that's currently in the file, or maybe you don't get rid of it, but you get rid of its meaning. Then there's append mode, which allows you to read and write. And then the R+ mode, where the file must already exist, but it still allows you to write. Okay. So how does the hierarchy actually work? Well, it works very similarly to anything else. There's a root node or root group that you can place other data sets inside of. So you can either specify this by the string /, or you can specify this as f.group. So if I go over here I can say f dot root right here on the command line, and I get my root group back. And it tells you what children are in there because previously this was from the warm-up, and we created that heart group. You can access in PyTables other elements of the hierarchy, much like you would access attributes on a class in Python, or exactly like that. So elements of the hierarchy become attributes of your Python object, or Python objects. So in this fictional example, you would go to the root group, and then from the root group you might have another subgroup, just called a group here, and then you might have an array called some data, and that would get you back that data. So this is what's known as natural naming, right? And this requires that all of the elements of your hierarchy have names that are only valid Python words, right? So that regular expression like /w or /w. So that means that it can only be uppercase letters, lowercase letters, and underscores for this to work. If you have elements in your hierarchy that do not follow that, maybe they have spaces or like some other ampersand or some strange character, PyTables won't freak out. It just won't let you access it in this way. There's other mechanisms of getting a hold of that data. There's a get node function that allows you to pass in a string that can have any character you want in it. Okay. So you can create new nodes in your tree relatively easily, but because you've got this root thing, which represents your hierarchy, basically all creation functions have to happen on the function object themselves, right? They can't function on the root group or data. They actually have to function on the file as a whole. So here we might say f.createGroup. Here you pass it the location where you want that new group to be made, the name of that new group, and then this is some metadata known as a title that lists it's more like a doc string than anything else. And then once you do that, you can access this through f.root.agroup. So let's go ahead and try this at the command line. Make sure you've got your temporary file object open, but please type along with me. So if you say f.root, sorry, I don't have two screens up. Oops, f.create.
It's readable only.
Yeah.
I think since the file is read-only, you'll be able to.
Oh yeah, that's probably true. So let's introduce another function here, f.close. Super sneaky, right? Then we'll go ahead and reopen this file. Let's reopen it in R+ mode, or yeah, let's open it in A mode actually. That's fine. So it didn't really matter. So let's go ahead and create a group, and let's just call this, as I said, a group. You can say happy group. And there you are. And then you can go ahead and access this as f.root. And in IPython, because there's tab completion, this will actually tab complete for you too, which is super nice. Okay. Everyone able to do that or follow? Okay. So as I mentioned before, the two most common data types, or data sets, excuse me, in HDF5 are tables and arrays. And we're going to treat those here. So as mentioned, all the create methods have to live on the they live on the file object. So here you have a create array function. You tell it where. Here we want to create this inside the group, so you give it the path to that. And then you tell it what you want that array to be named in this as the second argument. And then finally, you give that array the object that you want the values to be filled with. So here we're counting 1, 2, 5, 3. And this is just going to end up being an integer array because everything here, this gets piped through NumPy effectively. Or you can think of it that way. And every element here is going to get passed to an integer. Okay. Tables require a little more overhead. Basically, tables, because they're structured arrays, which actually, who knows about structured arrays? Okay, so it's most of the class. So tables, since they're basically just structured arrays, so they need a description or a data type. My preferred method of doing this is just to always go through the NumPy D types. There are other mechanisms of creating descriptions, but they're just not as refined, I guess. This is probably the best way that I've found. You can create descriptions from meta classes or dictionaries or other methods, but this is what I like to use. So here we're just defining a separate D type where our fields are going to be named ID and name using the NumPy mechanisms for saying how many bytes those each take. So this will be an int, and this will be a string of length 10. Then we can create some data just using a normal NumPy array of this D type. Here we have Lancelot and Bedivere. And then you just use this create table method on the file again. Very similar to what was happening in array. This gets, you say, okay, well, I want this to exist on the root group. I want it to be called nights. And you have to pass in the description to that table. So here we're passing in this data type that we defined, which is why I defined it up here separately, rather than defining it in line in this, like most people do in NumPy, they just define it here. That gets us an empty table of that data type. So if you want to stick data into that, you have to do something else. And here you have to, here we're just taking that table, that nights table that we created, and appending the nights data, if that makes sense. And that just gets shoved right in. Okay. Any questions about what was going on? Yeah. That said, arrays and tables try to preserve the original flavor that they were created with. Flavor is actually a term that was used, right? So up here we created a table with a list, and here we created one with an array. So when we try to grab those back out from HDF5, we would like to get a list back and an array back, right? And PyTables tries to do so. So here, when you ask for Arthur count, what you in fact do get is you get a normal Python list. And you can check that with any sort of type checking mechanism that you so choose. But if this was an array, you would have gotten an array.
You show the previous one right there.
This one? Yeah.
We'll, on the way out, in the case of NumPy arrays, we'll copy the name.
Well, so the HDF5 is on disk, right? So yeah, I mean, it's copying from disk into memory. Yeah.
So how does it keep track of whether it's used for disk or an array?
So this is a PyTables only feature. So in the metadata of that array or that table, there's a flavor attribute, an HDF5 attribute, and that stores I am of this type, and it knows how to decompose that correctly. So you can do a lot of fun. There's a lot of fun there that can be had if you want to extend that flavor mechanism. Okay. So we'll just go on. So if they come from NumPy arrays, for instance, you can access data from them using NumPy-esque slicing and fancy indexing and masking things. So here, even though nights itself is a table, if you ask for the first element, it's going to give you that first element back out. If you slice, it's going to give you an array. If you can create a mask, right, with that, I guess it's a little small here, but if you take the whole array and you do some comparison operation, you get back a Boolean array, and then you can use that Boolean array to index into nights, which will then, of course, give you another array back out. And finally, you can use fancy indexing as well. There's only 2 elements in this array, so it's not that interesting, but reorder them. Yeah?
How much of that is depending on NumPy, and how much of that is actually using HDF5?
The answer is neither, in fact. So both, well, it depends which, if you're dealing with a NumPy object, if it's already in memory, it's going to be a NumPy object, and that's dependent on NumPy. But in this case, right, this slicing operation is taking place on the HDF5 array itself, or HDF5 table itself. And to do that, you have to redefine what slicing means for that object, which involves going into the HDF5 spec and creating a hyperslab and pulling data back out and shoving that into a NumPy array.
Okay.
Yeah. So slicing, fancy indexing, and masking and everything is actually redefined for these objects if you're acting on the object itself, because it has to be.
Is there any way you can turn on logging? So, because like this works here fine, but I want to know what's going to go to disk and what's going to be in memory, and like if it's not clear, I can see how you're some trouble.
Yeah. So it's HDF5 as a whole, and pitables are not transactional. But there is some there's a verbose mode that you could set to at least get a printout when some things are when different functions are being called, if that's something that you really need.
Yeah.
But it's not going to take that operation and store it in some extra transactional.
Yeah, I was talking about that type of log.
Okay. Yeah. But yeah, good question. Okay. And when you access data in this way, it's known as memory mapping. I'm assuming you guys didn't get to memory mapping either last lecture. So that basically means that when you're pulling data out of this array, you're only pulling the data from disk that you asked for. You're not pulling the whole array. This gets back to your point. You're not pulling the whole array and then doing this indexing operation. You're only pulling the specific things that you want. Because the data is very regular and you know its stride and everything, and shape. Okay, so I felt like I just talked for a little while, but it's now time for an exercise. This one is called the Peaks of Kilimanjaro. So please go ahead and open up your, or go into your exercise directory as you so gracefully. So here I'm in my exercise directory. Gonna look at Peaks of Kilimanjaro. Oh, this is great. So let me read this to you and we can talk about it. So the prompt is that your brother is going on an expedition to build a bridge between the 2 peaks of Mount Kilimanjaro. He needs you to create a database of information about this team that he's assembling. So this needs to contain a table of critical team member information and an array of oxygen deprivation fractions to be filled in later. It doesn't have to have values in it, or meaningful values, for every team member for each of the million steps up the 1 peak, or up the first peak. The information that you need is their first name, their last name, their age, and whether they have survived or not. So that's parts 1 and 2. And then finally, he has forgotten the first half of his team's name, so please read off just the first half out of his library. Be careful out there. So here below, we've defined what what your team is named, like Brit Housemate. And go ahead, we'll give about 15, 20 minutes for this exercise, and I'll walk around and help if you have problems, and feel free to ask questions. And just fill yeah, feel free to execute these below if you get, yeah. But for time reasons, I'm going to continue on. So I hope you don't kill me. Climb the wrong peak. So let's go ahead and take a look at the solution. That's just in the Sol directory. This one is named, I have to update my slide. This one is just, it's named the same name. So let's go over how this works. So first, the first thing to do, of course, is to open a new file. Here I'm opening this in write mode so that I'm able to, in one terminal, just re-execute this file over and over again. Then for part one, which was writing these people out to a table, I create a D type of this type specified right. So here there's going to be a first name, which is a string of 10 characters, a last name, also a string of 10 characters, and then the age, which is of course an integer. Guess it could be a float if you wanted it to, and whether they are alive or not as a Boolean. And then I make a NumPy array of that with that data type using my original list up here. And then finally, I just call f, my PyTables file, .create table. I'm going to store that as the name T, or team, in the root group with these values. I'm just piping that array right into, you can also pass the table just the raw array, and it'll pick everything up as well. In the second part, we are going to make an empty array, or a zeros array, that has the shape of the length of the team times 1,000,000, right? There's 1,000,000 steps. And then finally, we're going to name that oxygen deprivation. And then we're going to store that oxygen deprivation array right also in the root group. And finally, I'm giving this a title, which is just help I can't read. So it sort of reinforced that docstring concept. And the new thing that I'm doing here, which I didn't talk about in the slides, is that if I ever want to ensure that the data for the table or any data set is written out at that point rather than just cached to be written out later, you can always call flush. And flush will take whatever's in your memory buffer and write that out to disk. Okay. And then for the first part, this is sort of a naive implementation, but what you can do is you can loop over all of the elements of team, getting your first, last, age, and alive back out as individual elements. And since alive is a Boolean, you can do a conditional on that and print the first plus last name. And then finally, we're going to just close out the file. Okay. Yeah. So to show you that this works, oops, I did not want to spell check. Thank you. Here we have, what is that? Shift control. Right there. Okay. So to show you that this works, I'm going to run my solution, peaks of Kilimanjaro here, and then finally it prints out the names of everyone in the top 5 who are left standing. And furthermore, if you have VI tables or HDF5, which I highly recommend, you can always, what I typically do is I'm writing the code, I make sure that I go and look at VI tables and make sure that it matches what I think it should be doing. So, sorry for having to navigate back here. So here's my expedition file, and you can see we have our team array, much like you'd expect, and we also have our giant oxygen deprivation with the title stored up here as well. Okay, any questions about this exercise? Yeah.
Yeah, so as you had to allocate the really big oxygen array, is there a way to create a big array like that without having to create another one first?
Yes, and we will be going over that in brutal detail. Okay, we're all good, yeah.
Also, if you have strings that you don't want to be fixed length,
Yeah.
how does it, what's the appropriate approach to doing that for HDF5?
So there's a VL string column here. So this is a pivot solution. There's like you can basically have a ragged array, right? You can have elements of you have a column that is declared ragged, such that each element can be a different size. And there's an atomic type for that you use. So that's how that gets handled. There's not really an analogous feature in NumPy, so I wasn't covering it immediately here, but it's something you can do if you want. Under the covers, it's basically it's doing a soft pointer to another part in memory that stores those like that section of bytes, right?
Okay.
And that column is a fixed size that tells you where to look. So that's how the nuts and bolts of it.
Thanks.
Yeah, no problem. Okay, black knight always triumphs, right? Great. Okay, so let's go on to talk a little bit about sort of the first section that I proposed, which is just some tips on how to lay out your hierarchy. So say you have a big table of people, right? Here we've got a bunch of people. You know, they have their names and professions and where they live. And this is fine, well and good, and especially in sort of a SQL-like paradigm, you might be tempted to just, you know, throw all people into a people table and just leave them there, right? Like that's what happens. Because everything exists in this flat namespace. And then you might look people up based on their profession and do a join or something later. But this is what you do. However, if you know, say you're always going to be accessing a certain class of people, you don't necessarily want to have to search through that table each time to find that profession. So here, what I've done is just separated out the knights from everyone else, right? So in fact, I have a knight table that if I just want to look at knights and I know I want to look at knights, I go to the knights table and just look them up. I mean, you can do this other places too, but the thing about this though is that when you name that knights table, that second profession column becomes redundant, right? So that's an extra level of storage that you no longer need. So if you're thinking about, you know, compression and access times and stuff, this is actually less size on disk, and it's faster to find because you're making some assumption about the data and the way the data is structured, and you can embed that information in the hierarchy itself. And that's that's the advantage of the H, right, in HDF5, is that you can put information there. You can go a step further with this too, since you can have sort of infinite depth here. Say you also wanted location information like England or France, you can embed that information in terms of where you look on your path for these people. So let's sort of grok that. Okay. So why bother doing this at all? That's a reasonable question. Well, I mentioned it's fewer rows to search over, fewer rows to pull from disk. You have this thing where you compress the number of columns that you need, and ultimately it's all about just making queries and everything faster. Okay, so if it's really about making everything faster, it's worth taking a little jaunt in terms of access time analogy, that in terms of like how long it takes to get data from one part of your computer to another. So if we just look at our processor and our L1 cache to begin with, if you claim that this is about similar to finding a word that you know is on your computer screen, maybe this is about 3 seconds. This is your L1 to processor cache. or processor access. Excuse me. Getting data from L2 cache to your processor is then sort of equivalent to getting up and getting a book off of your bookshelf, which is about 15 seconds. Going out to main memory for anything is more like going to the break room and getting some coffee and a candy bar, and talking to someone for a couple of minutes. Then, going out to your hard disk drive is like wandering the earth for a year and 4 months, right? And then finally, when you get back, your computer will have computed what you need it to. And since this is a file format, this giant gap needs to be crossed all the time. So you really do want to minimize the amount of times that you need to go out to your hard disk for anything. This is getting a little better with solid state, but it's still not. This is still a big gap. We're still on the orders of months here. And I'd like to thank Kurt for pointing out this analogy and the original author of it, because I think it's really good. So more formally, this is kind of known as the starving CPU problem, which basically means that because you don't have stuff in memory for your computer to work on, it's just sitting there idle for a really long time, and you're not feeding it instructions. So here, this is sort of the prototypical memory setup. You have memory and your hard disk and then your CPU. This is what we just described. And this is sort of a in the future kind of thing, or right now. Actually, I would just get rid of this mechanical disk at this point. So, yeah, the idea is that access times mean that your CPU isn't working, even though it could be. Okay. So we've covered arrays. Now let's cover tables in a little more depth. So tables are basically a high-level interface to an extendable array of structs. Really what they are is they're just normal arrays where different fields in your that you claim as a row have been assigned different meanings, right? So a struct is a very low-level way in C. There's a low-level way of assigning meaning to a field. A D type in NumPy is the same thing. It's the same thing with description. So going back to our another person example, say everyone has an ID and a first name and a last name. That ID might be an integer, which you might say, okay, well that's 4 bytes or something. I'm going to call that ID, and then I'm going to call the next 10 bytes my first name. And when I get that data back out, I know to cast it to a string, for instance. Data types, as well as structs and things, may be nested. However, they are stored in a flattened way. So to look at this example, we have this data type where we've defined ID, first, last, and parents. And then parents itself is another data type that stores IDs back to mom and dad, right? So these just are integers that go back to mom and dad, but they get stored in this other way. So here, if you were to run this command, you would be able to create a table of these people, and you would see that the data type gets nested. I think I can't copy and paste easily from this in presentation mode. Well, let's try it. There we go. Oh, not with that. Sorry. So I just uploaded the slides to GitHub, so you can go grab them there. But I encourage you to maybe try this as well. So I'm going to open up I'm just going to open up IPython here and import NumPy, import tables. Please follow. Oops. No, that was silly. then you do, just create a new file. We'll just call it temp.h5. Set up in a pen mode if it's there. No. Okay, so I copied and pasted this in. It executed. We can look at what people is right here, or our random people thing. And then we created a table just that was named random peeps. We can go then and look at VI tables. I'll just close this. And oops. I bet it's because I didn't flush or something. And then you see this to this random table, and note that at the top level, this is just known as parents, but it is in fact an array of length 2 of ints, and you could refer to those individually. Okay. Yeah. Yeah, and that's basically what you get. So the really nice feature about doing all of this in Python is in fact that you can declare these descriptions and their sizes dynamically. That's actually really, really very valuable. You can declare descriptions and sizes and things dynamically in compiled languages, but it's a little more tricky. And I'm going to go over that now if people are, well, I'll just go over it now for the couple of people who are interested. So basically, what it comes down to is that you need to create a struct and then over-allocate it, and be very careful about how you use the byte count from that point on. Because HDF5 itself doesn't care, it just cares about the total size and doesn't care what you stick in there. So however you decide to stick something in there, that's fine. But it's up to you to assign meaning to that. So here, let's say we have this struct. It's a material, it has some mass, it has the number of atoms per mole, and then it has a pointer to an array of doubles. So here, what you would do in HDF5 in the C API to be able to, if you didn't know the size of that component array a priori, but you wanted to compute it, that's this comp size thing that might get passed in elsewhere. You would compute the total size of this struct that you wanted, and then you would create a data type that has that size. And here we're creating a comp type. You also create a component type that mirrors that. It's an array of that length that you passed in. And then you go through and declare the rest of the types and their offsets. And then finally, you over-allocate. Here we're using new C++, I guess. And then you can go ahead and fill that in any way you want, and HDF5 will accept that. But it just, you have to be able to, you have to declare that in this sort of roundabout way. In Python, you can do this very easily, as you've seen. You can change the byte size that you want to store. But it is possible. So files that you create with these random sizes in Python, you can read in and read out in other languages just fine. Very important. Okay. So now it's now time for another exercise. This one's called boatload. And we'll be mostly on tables. So go back into the extra directory. And open up boatload. All right, so we want to create a metric boatload of random people. So that's right, we want 1,000 people. You saw sort of an example of this in the slides. First, we want to define the description, and we want to know their names, their latitude and longitude together, the list of ships that they have sailed on, which is at minimum 1 ship, but maybe at most 5, and whether or not they've been lost at sea. Okay, so that said, once you've defined the description, use this rand sailor function that I've defined down here somewhere to create, or to write, basically create an array of all these random people, of 1,000 of them, and then write that out to a table using your dtype. Then, after you've done that, rescue patrols are typically dispatched by which 2 hemispheres they're in. So, northeast, northwest, and southeast and southwest. So, create these groups, and then inside of those groups, create smaller tables that represent just people who are at those locations. And then finally, they care about whether, these rescue patrols tend to care about whether people are lost at sea or not. So create 2 other smaller tables which have their status as whether they, in these groups, as whether they're lost or not. That makes sense. Okay. So you don't have to worry about this front matter right here. Just know that we've given you a file object, and here's where you start. Here's an empty place to find the description, and here's the sizes of the max sizes of the names, and go on from there. And I'll walk around. And then the type, right, as a tuple. However, this can also be a length 3 tuple. Maybe this will be, you know, we'll just call this home or something. Also int, but you can then, the next element can be the shape of that array. So here, if we wanted an array of ints that is length, 42 by 42, that's how we declare it. So this helps you out for the ships part in problem 1. There's other ways to do this in pi tables, but once again, this is what I use. This has to be a tuple, so if you just want a normal one-dimensional array, doing this in a one-dimensional form would be, okay, why don't we bring it back in, and so let's take a look at the solution here. So this is boat load. So in the first part, where we were to define the description, this I just used NumPy as data type again. So the first and last columns, last name columns, were going to be strings of the max length of the first and last names, right? So here I'm just calling string around those integers and adding it to, or concatenating it with the s. The location is a nested data type because we wanted latitude and longitude to be next to each other and have their own names, and these will both be floats. And then our ship's data type, as I mentioned, it's going to be a string of the max length of each ship name. And we, as I mentioned up here on the board, this is going to have up to length 5. So we're just going to declare it max to be that max length. And then finally a bool column at the end of the day. Okay. Does everyone understand how that data type works?
What would be the difference between doing the location with a float of two floats instead of nested?
You could do it that way. That's perfectly legitimate. The only difference is that then each of those floats doesn't get its own name, right? It doesn't get the latitude and longitude name. It gets an index, 0 and 1, which, ontologically that's a name as well, but it doesn't get the string human readable name. So this was just an exercise for nested types. But yeah, you could have done it with just all of length 2. Okay, so then we're going to create a array of sailors. So here I have some raw sailors, that just is a list. Going to call my random sailor function 1,000 times, and then if the ship's list that you get back out of that function is less than length 5, it's going to append a bunch of empty strings to that list. Okay? And then we append this tuple of our data back into the raw sailors. And then finally, we create an array of that using our description that we created above. And at the end of the day, stick that into a table. Everyone understand? Okay.
So if you hadn't done the ship.extend, would it just wouldn't work because they're not all the same length?
That's right. It would have been this data type that we described says you need an array or a container of length 5. So you better have a container of length 5. NumPy itself would actually catch that error if you tried to make it. These two temporary arrays for 256 that are 256 long, you're going to do those temporary operations on these smaller chunks, store those in separate locations, then do the addition operations on those arrays. Sorry, I used a semicolon to fit it on the slide. And then finally store that back in the location of that of the C array that matches that chunk. Does that make sense? So here we're doing this. We're sort of mixing what we did before, right? So we're not doing fully element-wise, but neither are we doing full array. We're operating on individual chunks. And because we needed a kernel for this is why it's called in kernel. This happens to be the basic idea behind the num expression package, which I'm not going to go into in greater depth in the next slide or two. But it's a really cool package. It's this virtual machine. It's a generic virtual machine for NumPy arrays. So if you need your calculations to be accelerated, or your NumPy, like large complex NumPy expressions to be accelerated, this is a great way of doing that. And the other thing is that this problem, right, because each chunk is individual, once again, not only on I/O, but also on these calculations, is also parallelizable in a very in a well-structured way. So num expression is, in fact, it uses p threads behind the scenes, and multi-threading. So here we are. And it avoids the GIL, which is always nice. On top of that, PyTables builds an expression class, and this back ends to that num expression virtual machine that we just described. But since it knows it's getting data off of disk and not memory, it knows how to optimize that as well. Okay, but it's the same interface, okay, except for disk. And therefore, that full array need never be read into memory, which I'll give you an example of here in a moment, or right here. So here's a fully out of core example, right? So say you have this shape, it's non-trivial. This is right from the PyTables docs. You've created these 3 ABC arrays in your HDF5 file, right? They've been defaulted to 1, 2, and 3 to have as their values, their fill values. And then we've also declared a C array. A C array is just a chunked array. We also declared a C array, which is our output that we want to be stored, where we want our results to be stored. We then give it this string expression, which knows the namespace. It gets executed in this local namespace, so it sees that these A, B, and C are here, and are PyTables objects. And then we can say where we want the output to go. Right? Nominally, if you don't set this output, it would just return a NumPy array in memory. But if we want to write, if we know we just want to write those chunks right back out to disk, it can write based on the chunk size, never bringing that full array into memory or having to reconstruct it. And then we evaluate that expression. Okay. So does that make sense? This is operating on arrays on disk and returning arrays on disk. Yeah.
So you mentioned both the writing and reading, and these operations can happen in parallel. Is that something that happens transparently based on?
Yeah, you don't have to worry about this at all. It just works. Yeah, but I mean, under the covers, what it's doing is it's doing all of these things in parallel. Or yeah, you can set the number of threads if you want. There's a parameters module where you can set all of this stuff, but you don't have to fiddle around with it.
So I'm just curious, like just some general guidelines. How big of a file would you want before you need to start considering these? Like when you know that it's going to start to slow down your NumPy array.
How big is your memory? Is the question.
Yeah.
Right. So if you're operating on like a data set that's a gigabyte, I would consider this. I mean, it's going to be, or even less. I mean, it's always going to be faster, but you absolutely need it at the gig, 4 gig kind of level. That should be, I mean, I should mention HDF5 scales incredibly well. You know, I've got data sets that I work with now which are in the hundreds of terabytes, but HDF5 goes up to, you know, a few petabytes. That's what it's been tested on, at least. It's actually hard to get resources for that, but as you might imagine. And it works in part because chunking works how it does. It was all enabled.
So back to your previous point, does the NumExpert use of Pcos depend on a multiple NumPy, or is it part of the NumPy?
No, so it's actually independent of NumPy's compilation. So these are independent C extensions. Yeah. Yeah. Okay. Yeah.
So what is the performance difference that you typically see?
We'll get to that.
Okay.
We might get to that.
Okay, cool.
Yeah, we'll get to that later.
Great.
Yeah. There's a really great page on our documentation that has graphs that you can steal explaining this, which I have stolen for some part of this later.
Great.
We might, yeah. Actually, I think now it's about 3 o'clock. We're scheduled to take a 15-minute break. And I think now's a good time before I jump into querying. So that's right, Darhash, it's 15 minutes. Okay, so 15 minutes, be back here at 3:20. Well, let's go ahead and get started again. Is there a way to turn down the lights there? Is there a light?
Try swag.
Yeah. Almost worked.
All right, it takes a minute.
Takes a minute.
Yeah.
It's a slow clapper.
Hey.
All right. Let's go on. So the next section, we're going to be talking about querying. So oftentimes in databases, right, especially those people who have ever used SQL, querying is something you do a lot, right? Basically, you have this file or you have this database, and you want to ask it some set of questions, and get back the results that match the criteria that you gave it. This is sort of globally known as querying. And you typically query on data sets, right? You don't query the file as a whole. Because querying is very, very common, it's something that you want to do all the time. There are special methods for doing so in tables. These do not necessarily come, lock, stock, and barrel with HDF5. This is added functionality. So these are the where methods. So and they're defined on the tables, on tables themselves. So there's the normal where method, which checks or which evaluates a condition and returns an iterator over the rows that you can then stick in a for loop or list comprehension or something. Then there's the get where list, which evaluates the condition and gets you the indexes of where that condition was met. The read where, which evaluates the condition and returns you a list or an array or something that matches that condition, so you don't have to go back through. And then the where append, which allows you to evaluate a condition and then append the results of those rows directly out to some other table. So that's the destination table. As long as that destination table matches the description of the table that you're in. So this would have been a simpler way to do the sort of thing that we did in the boatload exercise, right? You want to evaluate the condition of where people are, etc. Okay. So conditions used in where are basically strings, and they're evaluated by num expression or the expression class in a very similar way to what we just talked about. And with the added exception that these expressions must return some sort of Boolean, right? Before the expressions could be evaluated, it could be any other of the atomic types or whatever you wanted, as long as that, as long as it could return it, basically. Here they have to be Booleans. So this is similar to the masking concept in NumPy. Moreover, these where conditions, much like num expression, or as with num expression, are evaluated in the context of the table itself, so the columns get are valid names in that namespace, and in locals, and the union of locals and globals. So, and the where method returns this iterator, right? So here we'll say we have some hypothetical table out there in the world, and then we want to evaluate this string, which is, we're checking for column 1 wherever it's less than 42, and where column 2 is equal to column 3. So these would be our fields in our data type are named column 1, column 2, and column 3. Not very creative. But what that gives you is an iterator, which when you evaluate it in this for loop, you get a row back out. Okay. And then you can do whatever you want with that row once you have it. So as sort of a speed comparison, right? There's no reason that you would have to do this querying with the where method. You could just do this query based on iterating over every row in the table individually. And to do that, there's this equivalent, this is the equivalent Python, right? So here we have this list comprehension. You want to pull out column 2 for every row in this table if, and then here's this complex expression, right? Row column 4 is smaller, right? And this gets evaluated with whatever limit and everything else mean and how they're defined in the local scope. The equivalent out of core search is here, right? So here we're just using where, and we have to define the string, but then we can get rid of the row indexing operations and just use the column names themselves, and that'll get evaluated. So this gets evaluated by, this gets evaluated by num expression and does exactly the same thing. Okay, so how much better is this? Ignore all this stuff about the compression levels or whatever. For right now, just be interested in this blue line, or this, I don't know, cyan line probably, and then this dark blue line, and the comparison with Postgres. So in sort of normal Python, this is the timings that you get for the number of rows that you hit in a table with 10 million rows. This data size can fit in memory on the machine that was being used. The equivalent search using the where method, right, this is on a log scale, is about an order of magnitude faster. Just because it's doing all this parallelism and it's operating only on chunks and only small amounts, relatively small amounts of things are in memory. You can start evaluating this condition on one chunk while you're getting other data read in, the next chunk loaded in, crossing that world tour. And so there's a lot of advantages to using this where method just out of the box. And then equivalently, doing something very similar in Postgres, it's much faster than that too. It's about 5 times faster. Okay, so that's with something with 10 million rows. What if you wanted to do it with something that doesn't fit in memory? Here's that same expression for something with 1 billion rows, but once again, the where method, this in kernel thing, this blue line, is faster than the non-compressed version. To even get to do this in normal Python, you have to do some sort of trunking-esque thing, which is why these lines are a little closer. But there's still an advantage to doing it. Okay. All right. So any questions about querying or chunking or in-core versus out-of-core or anything? Yeah.
Just a quick question about the chart. What's the X scale? What's the number of hits, number of times you?
So yeah, that's the number of times that the condition evaluates to true per row. Yeah. I mean, as you'd sort of expect, because you have to loop over the entire table, this is going to be fairly linear or fairly constant, right? Postgres does some weird things when you get almost the entire table hit, apparently. But I'm not an expert in Postgres, so don't ask me one. Or you can ask me, I just won't know. Okay. Any other questions? Yeah, Eric.
So if you were going to try to do something across multiple machines, are you gonna? Am I forecasting what you're going to talk about later, or is that a reasonable question to ask here?
This is a reasonable question to ask here because I'm not going to be able to talk about it later for time reasons. So multiple machines is an interesting problem. You pretty much have to use HDF5's MPI layer. So they have MPI. Like the HDF5 parallel is based on MPI, and this is how all the big supercomputers do it, right? They call out, it sort of knows where all the data is stored across the memory of multiple different nodes on those machines.
But it's still kind of one virtual file.
It's one virtual file, that's correct. Yeah. So it depends what you mean. It doesn't support that kind of like you would not be able to write out. So writing is much more difficult than reading. So you would not be able to write out to a file like that. You would be able to read from a file like that in parallel. And actually, you can read in parallel even with a normal HDF5 file just using a thread pool or a multi-droplet pool very, very easily. Like that's not hard. But yeah, like these big custom architectures and stuff, things get weird, and that's a whole other set of.
And so, are there examples of where you would do this square thing using kind of a map step? Kind of calculate where, I mean, you're doing a map.
Yeah, you're doing the map in a reduced.
So, are there examples out there of how you do this efficiently from Python on a parallel machine?
It depends a lot on your machine. So, we're talking about in the PyTables community of adding some of these examples because everyone has to roll their own, and it would be nice if there was like a place you could go that just had an example that you could pull off the shelf. And that works on the cluster-ish kind of level. But on the really big machines, they all have parallel file systems. And so as an end user, you don't even worry about it, right? You treat it just like a normal file system.
Yeah, there was a gentleman in the last class that was asking about Hadoop. They have clusters that are DoD machines that are all Hadoop based, kind of. And he was asking about this, and it got me thinking, how does this fit? And it seems like it should, but I'm not knowledgeable enough to say.
It does, but you have to do some work on your end. We're going to add it, but it's not there yet. So we're going to add examples, I should say. So, and maybe hopefully something in the future that gets wrapped up in this more. We put in a proposal to do something like this, but DOE didn't fund it, so here you go.
Okay.
That's a short answer. DOE didn't fund it. Yeah, we can talk more later. Okay, so now time for the next exercise. So this one's called chrono.py. Okay, so go ahead and open this up. So the prompt for this is that your friend Chrono has been murdered by the mighty demon Lavos. I hear some chuckles, which means it's a good sign. Luckily, you have a time machine, the good ship Epoch. You and your friends hatch a scheme to save him by replacing him with a doll that looks just like him. Unfortunately, Chrono also had the time machine before he died, and you're not exactly sure when he died. Thankfully, the Epoch has a log of everyone who visited all time periods and whether they were alive or not. All right, so to save Chrono and foil the plans of the mighty Lavos, you must do the following things. First, you need to search through the ship's log and print all of the times that Chrono was alive. Okay. Then you need to figure out if you ever left Chrono alone, and if so, when. Then write these times out to a separate table without fully reading the log into memory. Then you're going to send 3 of the friends of your choice into the fray to help Chrono out in his time of need. So do some sort of modification to the indexes of the log where he was alone, if he was alone. And then you need to figure out who Chrono's best friends are and who his worst friends is, and judge that based on the amount of time they spent with him. The situation is this. When you run this file, it'll make the epoch.h5 log. And then here's a list of his friends' names. You'll have to inspect this file and figure out what the data type of that, where the log is, and what the data type is. And then just run through these steps in order here. And then finally, there's a close statement at the end. Does that make sense to everyone? Mm-hmm. All right. It's a 20-hour game. So we'll give about 15 minutes for this. Or so. Then in the next part, you want to figure out whether Chrono was ever left alone, and if so, what times. And you want to write out those times to another table. So figuring out whether Chrono was ever left alone, first we're going to create this other table called Chrono Alone. And we're actually going to steal the description from the log, right? You can do this, the description and the dtype of the table just live on the table themselves. You could have also said dtype here if you wanted. And then we're going to construct this condition for when Chrono, right? You may have noticed, all of these all of the columns for all of the his friends and himself are Boolean, so you can just act on those directly. So you say if Chrono and not basically everyone else, and you get this string that looks like chrono and not friend 2 and not friend 3. And then we're going to use the where append method to just copy all of the elements of log that where chrono was alive but no one else was into chrono alone. And then we're going to just check, is this length greater than 0? If it is, we'll print out he was left alone. And if not, we're going to say that he had some backup and was safe. Okay. Everyone get that? Okay. There are other ways of doing this, but the way for number 3, if we're going to send 3 of his friends in at the points when he's alone, we're just going to reuse that alone condition. And for every row where he's alone, we're going to set my 3 favorite friends of his to be there as well. And then we have to update that row to get it to write out. And then finally, to make sure that that change has been persisted, we're going to flush that table. And look at the solution here. So this was our spam filter. So just going past all the front matter here. First thing that we're going to do is we're going to create an HDF5 array, or an HDF5 file with that single emails. I chose to store this as an E array. Some people are choosing to store it as a table. That is fine. Oh, I bet that's your problem with storing it as a table, is that that field isn't named. Yeah, I'm almost positive. So what we do is there's a times function, or the time function, and first thing we create email from email array. I just have these numbers sort of constant defined up here so that I wanted to change on my code for the entire file. I'm storing this as uncompressed.h5, creating E array, extendable array, storing that in the emails thing. Here we needed to give it, E arrays require that you give them an atom. So here, my atom is just a string of length 4. And then it's going to initially have 0 elements, so that's the shape here. And since I know the original size, and one of the optimizations you can do is just pass it the expected number of rows. So what that does is that makes PyTables more intelligently pick the chunk size and other things, and that optimizes what the B tree for the chunks in that data set are like. And then you just append the emails list. And finally, you get your time delta. And then I'm going to print out how large this file is and multiply that time delta to make it in units of milliseconds rather than seconds. Okay. Understood? So that's the uncompressed version. The compressed version is basically the same thing. In actual code, I would make a function out of this, but here we're instead we're also creating a filter, or filters up here, initializing them to these values, and then we are sending these filters in with the E array, timing that, getting the size, etc. Same thing with step 3, except now our filter is BLOSK and comp level 5. Okay. In number 4, this is a little different. We have to redefine our emails array and set that fill value of our original function to be false so that it gets random bytes for every location that's spam rather than eggs. And then do the same thing and continue on. Okay, and then finally, or almost finally, we use our new emails array and do the same with BLOSK filters rather than uncompressed. And finally, we take those file names. We're going to open up each of those files, time how long it takes to read in that emails array, into memory, and then print that out. Okay. We're going to have something relatively similar to this, I should have. Yeah. Okay, so running this on my machine, let's look at this. It's chugging along right here. So let's analyze these results and get to the point that Perry was making about random data. So for the uncompressed array, the file is about 40 megabytes. And it took not very long to write, right? Only 50 milliseconds. Using zlib compression, zlib1 compression, we get that down to about 7 or 8 megabytes, or 7.5, or 7.5 to 8. But it took a lot longer to write that file. Using BLOSC, the file size is about double what it was with zlib, but on the other hand, it took about half the time to write. And then, so that's with very regular data, right? Because we have basically only 2 types of elements, so compression should be doing a champ job here, or relatively good. But if we have just random bytes wherever we used to have spam for this spam level, the unfilled array, right, this is exactly the same size, it's the same number of bytes. And it takes the same amount of time to write, no big surprise. However, the compression algorithms totally fall over when your data is completely random, right? There's just no way to, or almost completely random. So while this was able to sort of compress some of those eggs that were next to each other, right? Because it compresses on blocks. So it's a little smaller, but it took about the same amount of time to write. This would have taken much more time if you use zlib here, even though the compression would be nil as well. Okay. Then finally, on the other end of this, to read in the array is about the same time that it took to write, and it's faster to read it. Now we're reading the whole array, we're not reading in specifics. Sorry, we're not reading in just specific section. But you'll note that in BLOSC, when you got a lot of compression, it took longer to read in because it had decompressed. However, when you didn't get any compression, it didn't take that long to read in, or take that much longer. So, sort of the moral of the story is compression is really great, but it also depends on what your data actually looks like. And if it's completely random, it's not going to do anything. It's just going to add a little bit of overhead. So, okay. Any questions on this exercise? Okay. Let's, in the interest of time, let's go ahead and go over the solution here. So, I'm going to open up Dick's table. So scrolling down, for part 1, oops, I guess this is a little, my screen is a little too big, but no. The first thing that we're going to do, or that we have to do, is we have to munge this dictionary to or create this array out of this table, or out of this, an array out of this dictionary. So I chose to do that by first getting the items list of that dictionary and then sorting them just for stability or whatever reason. And then I'm giving that a D type that maps the IDs to strings and the groups to strings as well. So that's our D type, because we know both of these things have to be strings. In other cases, you might know different data types for the keys and values of your map. And then we're just going to create a table with that array and call that ID group method. Actually, pretty simple. This concept of setting keys and values to be defined data types is actually mirrored. This is a much better, it's mirrored much more closely in other APIs and other languages. So like the C++, for example, the maps, their keys and values have to be typed. So this is exactly what we're doing. We're just typing the keys and values. And reading stuff out of an array that's set up like this into a C++ map is actually a very easy operation and very natural. Then we're going to read back in that data. So we're going to open that file again, and then to get the new map back off of this, we're just going to call dict around reading in that array, and that'll generate a dictionary that's keyed and valued in the same exact way. And this is stable, it gets us exactly the same thing. And then you can use this to efficiently grab nodes using the getNode method, where the getNode method takes where the node is and its name. So this is just the key and the value, here, because of the way we set things up, it's the value and the key. But this gets you nodes much more quickly than having to search through all 100 or 500 groups or whatever. And the place where you might have to do something like this is, in fact, there's only so many children any node can have. It's a fuzzy limit, but it has to do with how big the B tree can get and still be efficient at finding things. So occasionally, if you have 20,000 or 200,000 children in any group, you need to add a level to your hierarchy just to make HDF5 work, because at that point, like the number of bits it takes to store the size of the B tree, the locations of the B tree, it's too big. So sort of a weird limitation that you occasionally run into if you're doing this in extreme. Okay, any questions on this exercise? Be straightforward. Okay. Well then, don't even bother. Very briefly, what did we miss in this tutorial? Well, we didn't talk at all about how you walk nodes in a consistent fashion. There's a walk nodes method. We didn't talk about file nodes. These are basically variable length string nodes that you can have the Python file interface defined in them. So like you can send it a string and say write and read, and there's seek and tell and all of that you would use, but it's an actual HDF5 node. So if you wanted to do the last example is a pickled Python object, you would probably use a file node.
Are file nodes PyTables or HDF5?
They're a PyTables thing, yeah. I'm 98% sure. We didn't talk about indexing, which is another one of those SQL-like features. It's very powerful. It's sort of recently been open source. We didn't talk about migrating to and from SQL. We didn't talk about how you store HDF5 and other database formats. Like say you want to like store an HDF5 file in MongoDB. We didn't go to that. We didn't talk about how you might store other things in other databases in HDF5 using a similar mechanism, inverse mechanism. And we didn't talk at all about sort of high-level hacks about how you might use HDF5 with these features as a file system unto itself, which all these things combined, you can sort of see how that's possible. Hint, there's an HDF5 or HD Fuse 5 project out there that does this. It's pretty cool. And finally, I'd like to acknowledge everyone who sort of made this presentation possible. So that is, the HDF group, my fellow PyTables governance members, so that's Josh Moore, and Antonio Valentino, and Josh Ayers, and of course the NumPy developers, I'd like to thank our symbiotic project, the H5Pi team. We swap code back and forth actually fairly frequently. These are the other bindings in Python for HDF5. And of course, the progenitor of this project, Francesca Scopatz. So he's really responsible. PyTables has been around now for 10 years, so all credit is due to him. And then shameless plug, if you want to join the governance team or you find something wrong, or you want to help out in any way, we're always looking for more people. So it's on GitHub, we're completely open source, and if you want to help out, that'd be great. And with that, I will take any questions you might have about PyTables or HDF5 or anything in general, really. So, yeah. Any questions? Yeah.
I have a, like, is there a model for metadata for nodes, like adding arbitrary metadata, like units, you know, the physical units of the data or things like that to arrays and stuff?
Okay, so you got me on the what we missed slide. I missed actually adding, talking about attributes as well. So with every HDF, very, very briefly, with every HDF5 node, groups, tables, arrays, whatever, there's 64K of space allocated for metadata. And this metadata is typed, etc., much like anything else. And you can have whatever, you can throw whatever you want in there, but this is attributes. They're called attributes. So in PyTables, you can manipulate attributes through the, on the nodes through the dot adders interface, or dot underscore adders, or add different ones. You can look it up, it's there. And you can access this in any regime. It's very portable. The thing to note is that relative to pulling chunks of data out of an array, which is really what HDF5 is all about, attribute access is slow. So don't store like speedy things in attributes. It's much better. For instance, if you want to store like a file as metadata, it's actually easier and faster to store that as a node, like an array of characters as another node, than to store it into an attribute on the node that you care about. Good question. Anything else? All right, well, with that, tutorial adjourned. So thanks for coming.